giant nuclear spacecraft, interplanetary mosquitoes, and space robot squids. It all sounds like something straight out of science fiction, but surprisingly, these were real projects that were actually developed, and many of them are even feasible. Today, the space industry might seem quite conservative. Chemical rockets, and more chemical rockets. Although, of course, there are some more interesting options, like ion engines, which are now used more and more often. I've had a separate video about them. There are also some interesting projects for scientific spacecraft, yet very few projects actually reach the final stages and become a reality. But that doesn't mean that those which didn't make it are infeasible. In the 60s and the 70s, when the space sector was actively developing, and people weren't concerned with things like, safety, truly crazy projects were being developed. Today, there are still plenty of unusual ideas, like the one that are supported by the NASA's Innovative Advanced Concepts program. Some older concepts, like the Orion projects, are often talked about, while others are much less known. In fact, I myself came across some of these for the first time while researching for this video. And of course, these projects are full of ambition. Some have very unique spacecraft designs, others have novel propulsion methods, and some just have an incredible scale. Today I decided to talk about several such projects that at one point were being developed, but unfortunately, or in some cases fortunately, never became a reality. I'm Andrei, and this is Cosmos Elementary. Of course, since the beginning of the space era, there have been so many ideas worth discussing that it is impossible to fit them all into one video. So if you like this video, I might make a part 2. Some of the projects we'll discuss now, even though they didn't become a reality themselves, had a significant influence on other already accomplished missions. Let's start with one such project. And the level of craziness needs to be increased gradually. Project MALLAR surprises with its appearance, but conceptually it is quite reasonable. Check out what the spacecraft was supposed to look like. The huge, oddly shaped wings are actually unfolding solar panels. The name MALLAR stands for Manned Lunar Landing and Return, and it was developed back in 1959. The system consisted of 3 modules. One module was to enter lunar orbit upon reaching the moon, while another module would descend to the surface with 2 crew members. Doesn't it remind you of anything? Well, it sounds like I'm describing Apollo, which did go to the moon. And that's not a coincidence. Although the full design of the MALLAR project was never realized, its ideas were eventually, after a few iterations, incorporated into Apollo. Particularly the concept of a multimodal spacecraft with a detachable landing module. And since we're talking about the moon, imagine you're on the moon's surface. After a long research shift, walking around, collecting samples and all that, it's time to head back home. You're eager to get inside the ascent module. But climb onto the open platform and take off just like that. Because you were lucky enough that out of all the projects, they chose the non-pressurized version from NASA's Langley Research Center. Imagine taking off from the surface of the moon while just simply standing on an open platform. This concept, by the way, is quite recent. It was proposed in 2019 as one of the design options for the landing module for their Artemis mission, which aims to return humans to the moon. And this is the kind of project you get when you try to make things as simple and inexpensive as possible. There's a small pressurized living compartment where you can be without a spacesuit located between the fuel tanks. However, there's something missing in this picture. Oh, yeah. The airlock for exiting to the outside. And indeed, it's not there. So how do you get outside? Through your suit. The proposal here is to use an alternative airlock technology where the suit remains outside and is attached to the wall of the module of a spacecraft or a large rover that is pressurized. The astronaut enters the suit through the special port in the suit's back, then the suit is sealed, and the necessary pressure is created and the astronaut can walk on the moon. But during launch, in this case, the astronauts would remain in their suits and would essentially just be standing on the platform in the open space. Small shields would be needed to prevent the engine exhaust from burning them. It would be certainly an amazing sight for astronauts during launch, but it's not surprising that this project didn't progress further. And here the situation is quite the opposite. Unlike the Apollo Ascent module, the lunar rovers used by astronauts were not pressurized. By the way, if you haven't seen these, there are enhanced, stabilized and upscaled videos from the moon's surface, including rover rides. Make sure to check them out, I'll leave a link in the description. NASA had another lunar transportation project called MOLAB. This isn't just a vehicle, it's a complete mobile laboratory, as the name suggests. The project was developed in the early 1960s, before the first Apollo missions. The use of such a rover was considered for long-term stays on the moon. The mobile laboratory would maintain pressure and conditions in which astronauts could stay and work inside without having to wear their spacesuits all the time. Inside it would be equipped with a full range of instruments and tools for on-site sample analysis. With the mobile laboratory, you could venture away from the base for up to 2 weeks, live inside and explore the lunar surface. As you might have guessed, the mobile laboratory unfortunately never made it to the moon, as plans for long-term stays on the surface were scrapped. However, one functioning prototype was built and, in a sense, was even used for its intended purpose for a period of time. The wheel laboratory was handed over to the US Geological Survey, which used it in several research projects in deserts here on Earth. It certainly looks cool and retro-futuristic. I'll leave a link in the description to a 5-minute video showing the lab driving through the desert, including a look at its interior. And now let's shift our focus from the moon to other bodies of the solar system. Now let's look at some unusual examples of robotic spacecraft. What about a space mosquito? This spacecraft resembles a mosquito not only in appearance but also in its functionality. The concept is called Kuck's mosquito, named after its inventor David Kuck. The design of the spacecraft is quite simple. Essentially, it's a rocket engine with a large bag attached, along with a drill and a pump. And the spacecraft sucks. I mean, literally. The spacecraft is designed to approach small ice-rich bodies, such as comets, certain types of asteroids, and small planetary moons. It would drill into the ice, melt it, and then suck it up, filling the bag. A space mosquito that sucks water from comets. It's a service robot designed to supply water to larger space missions. And the water could be used by humans, well, as water, and also for producing fuel and oxygen for breathing. Interestingly, the idea was not completely discarded and could still potentially be used in future space missions. Another concept inspired by Earth's animal life is Squid robot, which I mentioned in the beginning of the video. Here the influence of real animals is evident not just in the appearance but also in the design of the spacecraft. The device is a soft robot intended to swim in the subsurface oceans of icy moons, with Europa being the primary focus. The body of the spacecraft should be soft and capable of changing shape, with tentacles used both for energy production and propulsion. It is certainly unusual. Given that solar energy is unavailable beneath Europa's ice, one could consider a radioisotope generator like those used on the Curiosity and Perseverance rovers and some other interplanetary spacecraft. But the creators of this concept decided to take a different approach. They planned to generate electrical power for the spacecraft using a specialized electrodynamic tentacle. Europa's orbit is within Jupiter's powerful magnetic field. At the same time, the planet's magnetic field is tilted relative to the planet's equator and to Europa's orbital plane. This means that as Europa moves along its orbit, it passes through regions of the magnetic field with different properties. In other words, a changing magnetic field. What does this mean? It means that, according to Faraday's law of electromagnetic induction, a changing magnetic field generates an electric field. If a conductor is placed in such a changing magnetic field, an electric current will appear in the conductor. The electrodynamic tentacle serves as a such conductor. This allows the spacecraft to generate electricity, but that's not all. The electricity not only powers the spacecraft subsystems, but it is also used to electrolyze water, creating a mixture of molecular hydrogen and oxygen. This mixture would then accumulate inside Squid's tentacles and be ignited, resulting in propulsion. In other words, the ignited gas expands, causing the Squid's tentacle to move, thereby propelling it forward. The spacecraft would move not with propellers or jet thrust, but almost like a real squid. The technology has already been tested in the lab. I've shown some footage of those tests. The project, developed at Cornell University in 2015, advanced to the first phase of NASA's Innovative Concepts program and received a grant. There's a detailed document in this, and as always I'll leave a link to it along with all other sources in the description. We probably won't see this project become a reality anytime soon, unfortunately. We're not likely to land a spacecraft on Europa for decades to come, let alone deploy something like this. But it's an interesting project anyway. The next project is also partially inspired by Earth's nature, but this time by plants rather than animals, specifically by dandelions. Meet the Windbot. Just like the Squid, both its movement method and energy generation method are unconventional. We really want to study atmospheres of gas giants in situ. For now, we do this using orbital spacecraft like Juno, or by sending probes into the atmospheres at the end of their mission, like the Cassini spacecraft. Or specifically designed descent probes like the one that was a part of Galileo mission studying the Jupiter system. Although the probe descended about 150 kilometers or 93 miles into the Jupiter's atmosphere and collected unique data, it operated for only about an hour. It wasn't designed to stay in the atmosphere longer. It was simply falling, taking measurements along the way. However, the creators of the Windbot concept are trying to address exactly this problem. They aim to ensure that research spacecraft can stay in the atmosphere of gas giants for as long as possible. A dandelion seed spins as it moves with the wind, which allows it to stay in the air longer. The Windbots are proposed to have blades installed on different sides to create lift regardless of the wind direction. Another key factor for energy generation is the turbulent atmosphere, where the wind direction is constantly changing. If the wind were constantly blowing in one direction, it wouldn't be as effective. If the bot were constantly being tossed around, it could generate energy in the manner similar to wristwatches that charge while the wearer moves their arm. In principle, such a bot could stay in the atmosphere for a long time, with its instruments powered by the energy from the turbulent atmosphere. Currently, the final design of this device is still a long way off. Research is needed to understand the conditions in the Jupiter's atmosphere and determine if the concept will even work. This involves figuring out the appropriate size for the bot, building a model on Earth and testing it in a specialized chamber. All of this is detailed in a comprehensive document. The project did receive a grant from NASA in 2015 for initial research. If Windbots could be created, it would be amazing to launch several of them into Jupiter's atmosphere. This would allow for simultaneous measurements from different points, providing a better understanding of the giant planet's structure. Now let's talk about something bigger. Perhaps some of you have heard something or read about the Project Orion. Not the Orion that flew to the moon as the part of Artemis mission. The Orion from 1960s. The old Orion would have given the new one a run for its money if it had been built. The project was developed over many years at the highest levels, with detailed plans and calculations. There are still opinions that such a spacecraft could have been built back then. Its capabilities would have far surpassed those of any modern rocket. But no space agency or company is rushing to use nuclear bombs to accelerate spacecraft just yet. The Orion project was developed in the 1950s and 60s, although the idea of using nuclear explosions for propulsion existed even before Orion. But why even go to such extremes? Even today, with the engines used for space travel, we have two main options. Either chemical rockets are used, where chemical reactions between fuel components accelerate and expel the propellant through the nozzle, propelling the spacecraft forward. The advantage here is that a powerful thrust is generated. sufficient not only to accelerate the spacecraft in space, but also to launch it from the Earth's surface and overcome our planet's gravity. But chemical rockets have a low specific impulse, meaning that they are not very efficient. They quickly burn through fuel, achieve a certain acceleration, and require a lot of fuel. Another option is electric engines, such as ion thrusters. They use electricity to accelerate the propellant to generate thrust, with the electricity coming from sources like the sun rather than the fuel itself. These engines have a high specific impulse, meaning that they can achieve high speeds with a small amount of fuel. However, they accelerate very slowly and have very low thrust, so modern versions cannot lift a spacecraft from Earth's surface. Thus, a chemical rocket is still needed to launch a spacecraft equipped with such an engine into space. Both methods allow modern spacecraft to reach outer planets over many years. But where do we have a lot of energy? In an atom. Why not harness this energy to accelerate spacecraft? In my recent video about surviving the lunar night, I talked about using radioactive isotopes for heating and powering instruments. And I also mentioned that using the immense energy released from splitting atoms, as we do on Earth with nuclear power plants, is problematic for space applications. But there I was specifically talking about generating electricity, and now we need to create thrust. Creating thrust specifically by heating and accelerating the propellant directly through nuclear reactions has been attempted in various projects of nuclear rocket engines. They have never been used in space yet. They seem like they should be very powerful and provide significant acceleration, but there is a catch. While a lot of energy is produced in fission reactions, it also generates extremely high temperatures. It means that everything would melt if the temperature exceeds 3000 Kelvin, or about 2700 degrees Celsius, or almost 5000 Fahrenheit. Therefore, efforts are made to ensure that temperature does not exceed this threshold, which results in the specific impulse of these engines being higher than that of conventional chemical rockets, but not as much as one might expect when hearing nuclear rocket engine. In reality, it's only a few times higher. And here comes the nuclear pulse engine. Its advantage is that it is impulse-based. In a nuclear rocket engine, the reaction occurs continuously, and the risk of melting the spacecraft structure by exceeding the critical temperature is high. Here, the high temperature exposure is brief. The spacecraft structure can withstand even higher temperatures. Interestingly, here, a parallel can be drawn with the conventional internal combustion engines in cars. In those engines, peak temperatures can exceed the melting point of the metals used in the combustion chamber, but cooling systems and the brief duration of peak temperature prevent the metal from melting. The Orion project was the first serious attempt to design a spacecraft with a nuclear pulse engine. Many of you have at least heard a brief description of how such engines work. Essentially, the spacecraft periodically ejects nuclear bombs behind it, which explode at a certain distance, pushing a special plate mounted at the tail of the spacecraft and accelerating this ship. But there are some details that need clarification. More conventional rocket engines, whether chemical or electric, operate by expelling accelerated mass propellant from one end of the spacecraft. And since the mass exits the spacecraft in one direction, it causes the spacecraft to move in the opposite direction. This is due to Newton's third law of motion, which states that for every action there is an equal and opposite reaction, and the conservation of momentum. I've mentioned this several times and also demonstrated by throwing a weight while standing on a skateboard, which caused me to move in the opposite direction. Yes, on Earth I can also push off the ground with my foot, and birds can push off from the air. However, in space we obviously cannot do that. So how does acceleration occur with bomb explosions? Besides the bomb itself, a propellant is also required to transfer momentum to the spacecraft, meaning it has to push and accelerate the ship. In early versions of pulse detonation engines, it was proposed to detonate bombs inside a special chamber, where water, which would serve as a propellant, would also be injected. In 1955, Stanislav Ulam and Cornelius Everett discarded the explosion chamber and proposed their more familiar variant, simply ejecting and detonating bombs at the distance from the spacecraft. Following the bomb, solid disks would be ejected, which would vaporize from the explosion, turning into plasma. This plasma would then push against the plate and accelerate the spacecraft. The advantage here is that, since the explosion does not occur in a chamber, more powerful charges can be used. And a little later, in 1958, the Orion project was born at General Atomics. In Orion, there were no separately ejected disks. Instead, the bomb and the propellant were combined into a single casing. Here is an example of a diagram for a charge in the Orion project. You can see the nuclear charge itself, and here is the propellant, which could have been something like polyethylene. As I mentioned earlier, today we typically choose between the high thrust of chemical rockets or high specific impulse of electric engines. A nuclear pulse engine like the one in Orion would offer both advantages. Both the thrust and the specific impulse would be several times greater than what chemical rockets are capable of. Another crucial component of Orion is the shock absorbers. Without them, people wouldn't be able to withstand immense g-forces. The temperature of the plasma pushing the plate would be immense, reaching up to 80,000 degrees, but the impact would be brief and it would only vaporize a thin layer of a special coating. Another well-known name involved in the project was Freeman Dyson. In fact, the team working on Orion saw themselves as direct competitors to Wernher von Braun's chemical rockets. Proponents of Orion believed that chemical rockets were significantly inferior. They could lift only a small amount of payload into space. Even modern heavy and super heavy rockets that have already flown can lift only 100 to 130 tons of payload to low Earth orbit. And if we're going further, like to the moon, the payload drops to just a few dozen tons. A typical Orion design back then promised to deliver hundreds of tons not just to the moon but to other planets. In some variants, it even promised thousands of tons. This would have eliminated the need for complex protection and life support systems designed with strict mass constraints. The spacecraft could comfortably accommodate crews of 100 to 200 people, and what a contrast to what we have today. Dyson and others were very optimistic. They believed that by 1964, Orion could transport a large human expedition to Mars. Not just Mars. By 1970s, they planned to send people to Saturn's moons. The journey would have taken several months rather than several years. Blueprints were developed and some test models were even built on Earth, and it was fundamentally demonstrated that such impulse-based acceleration could be stable. There even was a consideration to launch such a spacecraft directly from Earth. It would be launched from a test nuclear range. At the start, charges of 0.1 kilotons would explode every second, and as acceleration increased, the explosions would become less frequent but more powerful. But in the end, NASA preferred the more conservative chemical rockets of von Braun. And it's not hard to guess why. The whole nuclear thing, you know? There were calculations that launching from the Earth's magnetosphere could lead to radioactive contamination and the death of at least a few people. This could be avoided by assembling and launching the spacecraft from beyond the magnetosphere, but then it would still need to be transported into space and assembled there. After NASA's choice for chemical rockets, the project continued for a while, but the main reason for its cancellation was 1963 treaty signed by the USA, Britain and the USSR, which banned nuclear tests and explosions in space. There were various ship designs, including projects for massive interstellar spacecraft. Around the same time, other engineers proposed different ideas for spacecraft with nuclear pulse engines. For example, there was the Aldebaran spacecraft by Dandridge Cole. Here is an illustration of this massive design. It was intended to take off from the water, drawing in air like a jet engine during launch. This air would then enter the explosion chamber, where nuclear charges would detonate every second, hitting and accelerating the air to create thrust. I haven't found any information on what propellant the spacecraft would use in space instead of air. It is possible they might have considered injecting water into the chamber or using some other substance. Cole believed that by 1980s, such spacecraft would regularly lift 27,000 tons of payload to low Earth orbit and deliver 20,000 tons to the Moon. Cole used an explosion chamber because he thought that Orion project was using the explosion energy inefficiently. However, he apparently wasn't aware that Orion had already developed charges where the energy was directed more efficiently, so the Orion variant might still be a better option. It is frightening to even imagine what the launch of such a monster would look and sound like, not to mention the consequences of radioactive contamination. It was generally believed that with the materials and technologies of that time, Orion could indeed have been built. Interestingly, it is easier to imagine it being constructed then rather than now, even considering more modern technologies. Just then, there was a different perspective on safety and all that. It is interesting to think about how space exploration might have developed. But who knows? Maybe similar concepts may still be used for some interstellar spacecraft someday. They certainly won't be launched with explosions from Earth, but after assembly in orbit, why not? Unlike, let's say, warp drives, this is at least a genuinely feasible way to achieve significant speeds in space. As I mentioned at the beginning, this is far from all the interesting projects I have in store. If you enjoyed this video, I might do a part 2. In general, it is very interesting to see the scale of ideas from engineers and scientists at the dawn of the space age, especially given how conservative things are now. It is hard to imagine a project like Orion being developed at a high level for several years to date. Thanks for watching. Links to all of the sources are as always down below in the description, and if you enjoyed the video, leave a like, comment and subscribe for more videos in future. Bye!